single line to ground fault constitutes almost 70% of faults occurring in power system. Hence, we will limit our discussions to this problem only here. For analysis of L to G fault, positive, negative and zero sequence networks are connected in series as shown. Positive sequence network is shown at the top with voltage source. Negative sequence network is shown at the middle. It is same as positive sequence network without voltage source. Zero sequence network is shown at the bottom. There is no voltage source, even in zero sequence network. Depending on type of grounding, value of Zn will change. Since sequence impedances are connected in series, Ia1 equals Ia2 equals Ia0 equals Ea1 divided by Z1 plus Z2 plus Z0e. Z0e equals Z0 plus 3Zn. Most important, single phase fault current IF equals 3Ia0. Why the impedances are connected in series? How these expressions shown are derived. To understand these, you can refer any textbook on power system analysis. Some well-known textbooks are recommended at the end as reference material. But at this juncture, simply mug up these equations and try to know by heart. In case of ungrounded star or delta connected system, Zn equals infinity. Therefore, Ia1 equals Ia2 equals Ia0 equals 0. Therefore, fault current IF equals 3Ia0 is also 0. There is no ground fault current, an expected outcome, for ungrounded system. We will illustrate application of sequence network interconnection to find ground fault current in case of line to ground fault, with two examples. The first example is shown. Consider 10 MVA, 6.6 kV generator. Positive sequence reactance, X1 equals 25%. Negative sequence reactance, X2 equals 35%. Zero sequence reactance, X0 equals 10%. All the above are on machine base MVA of 10. How these values are obtained? You will learn more about them in generator module. Generator neutral is solidly grounded. Problem. For a L to G fault on phase A of generator terminal, find the fault current IF that will flow and the voltage of unfaulted phases VB and VC during fault. Phase A is shown red, B and C phases are shown in yellow and blue. You must be familiar with basic steps in fault level evaluations by now. First step is selection of base MVA, which is machine rating, that is, 10 MVA. Base voltage is 6.6 kV by √3. For line to ground fault, sequence networks are connected in series, as shown. Voltage source Ea1 is fixed as 1.0, assuming alternator is on no load, before the fault has occurred. Positive sequence impedance, Z1 equals X1 equals 0.25 per unit. Negative sequence impedance, Z2 equals X2 equals 0.35 per unit. Zero sequence impedance Z0 equals X0 equals 0.1 per unit. As neutral is solidly grounded, Zn equals 0. The major parameters are repeated for ready reference. Consider all impedances as pure reactance. Only Jx terms are retained. Resistance is ignored. It makes hand calculations simpler. Source voltage. In positive sequence network EA1 equals 1 per unit. IA1 equals IA2 equals IA0 equals 1 divided by Z1 plus Z2 plus Z0. That is, minus J1.43 per unit. Fault current IF equals 3 IA0 equals minus J4.29 per unit. To find fault current in actual amps, we need to find base current first. Base current IB equals base MVA10 divided by root 3 into base KV 6.6 equals 0.8748 kA. Fault current IF equals per unit current into base current equals 3.75 kA. Since this is the first time you found fault current for line to ground fault in this module, try to go through the steps involved once again. Will you? We have answered first part of question, finding fault current IF. Let us now find voltage of unfaulted phases. As a first step, find all sequence voltages. Positive sequence voltage VA1 equals EA1 minus IA1 into Z1 equals 0.643. Negative sequence voltage VA2 equals minus IA2 into Z2 equals minus 0.5. In the previous slide, we calculated in per unit. IA0 equals minus J1.43. VA1 equals 0.643. VA2 equals minus 0.5. Let us now calculate zero sequence voltage VA0, which is equals minus IA0 into Z0. Z0 is J0.1 and Zn is 0, as neutral is solidly grounded. Evaluating the expression, VA0 equals minus 0.143. We have studied in previous module how to reconstruct phase voltages from sequence voltages, using the matrix shown, and operator A. From the first equation in matrix, VA equals VA0 plus VA1 plus VA2. VA0 is minus 0.143. VA1 is plus 0.643. VA2 is minus 0.5. Sum VA equals 0. The result is obvious. Phase A is the faulted phase, and its voltage has to be 0. Next, we will consider second equation of matrix. VB equals VA0 plus A square VA1 plus AVA2. We have studies in previous module that A is minus 0.5 plus J root 3 by 2, which is 0.866. A square is minus 0.5 minus J 0.866. Substituting the values, we get the expression shown. Further simplification leads to VB equals 1.01 angle minus 102 degrees. Now we will consider the third equation of matrix. VC equals VA0 plus AVA1 plus A square VA2. Substituting the values, and after simplification, we get VC equals 1.01 angle plus 102 degrees. The positions of phases VB and VC are as shown. Voltage magnitude of unfaulted phases, B and C, is 1.01 per unit, hardly any change from nominal value of 1 per unit. This is as expected for solidly grounded system, in which voltages of unfaulted phases remain almost near nominal value, for line to ground fault.